Okay, so today we will talk about I think a very interesting project that is called relying on RER for DDoS attack protection. DDoS is something not new, but things is that we are getting more and more tools to prevent and help us to overcome this kind of issue. Today, David Schmitz from LRZ University Research Center in Germany and Nikos from University of Athens in Greece will present the work we are conducting under GÉANT 5 work package 6. That's which is a code name. If you don't remember it, it's not an issue. Before starting, I just wanted to present you a 10,000 view of our approach with respect to DDoS mitigation infrastructure. We have basically two rough components. One that I'm calling a trigger component. Basically, this function is to detect unwanted traffic and identify them. When this is done, it uses a way to provide information to another component that is in pass, in our case, that will handle the effective mitigation of the traffic. So today, the front component that are used are a combination of R data plane and Freertr control plane, and the trigger component are Firewall-on-Demand and NeMo. Those two software are the outcome of another work package within the GÉANT project, and this shows a very, I think, a good cooperation between our activities. I was mentioning that we use an interface so that the two components can communicate, and basically we are using BGP FlowSpec, which is a standard. So what does it mean for you is that for any reason, if you don't want to use RAR Freertr, or you have another component that is able to ingest BGP FlowSpec and do the mitigation, this is possible. You can do your own box, A10, Cisco router, Juniper router, whatever. This is possible. So now that being said, David, the floor is yours.
Yeah, hi, thank you for the introduction. Yeah, stop sharing, good. I can start sharing. Yeah, thank you. Yes. Yeah, I'm David Schmitz from Leibniz Supercomputing Center, as said by Frédéric, and I'm the main developer and development coordinator of Firewall-on-Demand, but I'm also this year and this phase working in RER to see how we can integrate it with the RER, the Freertr, which Frédéric already mentioned. And here I will present how far we are with Firewall-on-Demand regarding this. And so for those who don't know Firewall-on-Demand yet, or just as a repetition, I will just introduce the tool a bit. Here, just a very general thing about DDoS attack. Well, that's why the reason why FOD exists, and was a NeMo. We just see the GÉANT network here, by a very simple schema of a single router, and we see an NREN connected to it via BGP, and we might a victim host within the NREN, and we have a DDoS attacker somewhere in the sorry. Yeah, if a DDoS attacker somewhere in the internet and performing a DDoS attack towards the victim via the GÉANT network. And of course, there are also legitimate hosts which try to connect to the NREN and more specifically to the victim. And as you know, the DDoS attack will at least constrain the network of the victim, or even make it unavailable, or it will might at least on the path to the victim cause congestion, especially to maybe in the local network of the victim, or for smaller NRENs, it could even congest the whole link from GÉANT towards. And so this is a problem. And So yeah, you see that the victim is attacked and the network, at least the local network, can be impacted as well. So that is why, as Frédéric already introduced, we have some tools. There are two different approaches, let's say, Firewall-on-Demand and NeMo. They are quite different. Firewall-on-Demand is, they use both FlowSpec as a standard, as Frédéric told, but FOD is more a small, simple tool, which makes it easy to deploy and easy to use by a user, and user means NREN NoC admin in the GÉANT context. And it's only about the mitigation part as far as the tool is concerned. The detection of a DDoS attack is actually has to be done manual or by other means. That's FOD. NeMo is a much more a bigger system, which includes the detection part and also controlled mitigation and integrated with the detection. We will see later. Yeah, and we in this phase, in this project here, checking how to use Freertr, on the one hand for testing and development, but also to use maybe later in production. It is the case that FOD in GÉANT, when it was developed more than 8 years ago, was tightly bound to this GÉANT's Juniper routers, and in specifically to that uses netconf to put the FlowSpec rules on the router. That was the case, so yeah, 1 year ago, still 1 year ago, when we started with the GÉANT 5. And the idea was to move towards a more general means for putting FlowSpec directly with maybe something like ExaBGP. And so we can use it with other types of routers. And specifically, Freertr is a very good candidate here. So you don't need a real vendor router like Juniper or Cisco or something else. You can just run locally on your computer. So Freertr is very nice. It is also used in some real hardware, but it can be, what we use it is mainly for emulation and demoing. And I will present this here now for Firewall-on-Demand. Just a thing for the name, that there is firewall in the name, but it's not a firewall in the usual sense, because it's only about DDoS mitigation. And so these rules, which are put by a BGP FlowSpec here, are normally not to stay for forever or for a longer time on the router, only as long as the DDoS attack is running. But that's the name, Firewall-on-Demand. Yeah, and basically the main feature of the service, the DDoS mitigation control, is given to the user himself to mitigate within the core network, that is the GÉANT core network, attacks towards his network. That means where the destination IP address of the attack is within his network. It's BGP FlowSpec based, it's multi-tenant, based on eduGAIN for those who use it. It is developed in the GÉANT project since more than 8 years. Yeah, and it can be installed by others and NRENs as well, or any other who wants to install it. It's open source, but it's used for the GÉANT FOD service instance since it exists. And yeah, it's long time productive. The users are the NREN NoC admins, as said, and it's continuously developed and supported in VP8 task 3 in the security work package. And that is done in tight collaboration with the GÉANT security team. And here on the right side, you see just the intro screen of the web UI of Firewall-on-Demand. Just still going into what is the benefit for a user. Actually, the user, without need to contact the GÉANT NoC, can start, stop, or even edit his rules to that is regarding his traffic. And that is done either manually via web UI or can be automated via REST API. And what it means, it's a flexible and fast mitigation. Because, you know, many DDoS attacks lasts less than an hour. and you want to react maybe in minutes, and so that's and even to times where probably GÉANT NoC is not available, maybe so out of service times, and so that's what FOD actually brings as a benefit. How is it basically done normally? If you as a NoC admin, as a user of FOD, go via the UI, you basically edit rules via this form page here, and what you have to specify is just FlowSpec, basically, and that means mainly to match an IP packet based on source and destination prefix and IP protocol, and in case of UDP and TCP ports or port lists, and fragment options if needed. And then you specify a mitigation, which can be currently drop anything with matches or rate limited to a certain rate limit. And then there's an expire time when the rule should expire, which is at max at 30 days after creation and activation. So that's just basically it's just FlowSpec. And to continue our example from the beginning, we have here still the attack ongoing, and here we see Firewall-on-Demand controlled by the FOD user, which uses a web UI or REST API to control FOD. And if he does so, he is able to define the rules, which we just saw before in the form page, and then it is pushed via netconf, or now it is possible via exabgp to a specific configured GÉANT router, and from there it is spread via BGP, as all FlowSpec rules, to other GÉANT routers, and so it's enforced there, and or even if defined or configured to the even spread to the other NREN, and putting rules on the routers there just by BGP. And that means that the attack is actually mitigated at the first entry point of GÉANT actually, and all the traffic which would go further down here is just eliminated. And so that's that's how it works. And when the attack then is mitigated and ongoing, in the current version via SNMP, actually a Juno-specific filter statistics stuff, which uses firewall MIP, is collected from the routers and by FOD, and the user can see statistics normally, and so he can see how the attack is ongoing. If the attack stops maybe after an hour or so, he would see a drop in the statistics and then could decide to deactivate the rule. So that's basically how the mitigation via FOD works if you use it only as a user. Here you can see an overview screen, just an example of all the rules the user has defined. They can be active, that means they're on the router and spread via BGP, or they can be just deactivated and they are only in the FOD database and can be reused later. So what we specifically done since some years is we support Docker container with FOD, mainly for reference installation and also for development and testing. And with what we have done in context of the RARE project since beginning of the year is how to combine it with Freertr, as said before. And for this purpose, we have come up with a Docker Compose specification, which contains an FOD container, which is supporting the new exabgp stuff, together with a Freertr router, which is BGP peering with the FOD as exabgp. And we have two hosts in the Docker Compose set, an attacker and a victim host, which are connected via the Freertr router. And yeah, if you want to try it later yourself, you can find these references here for the Docker Compose set and some info if you want to debug it in detail or so. And what we've done based on the Docker Compose set is we came up with a demo script which I want to show you right now, which actually runs in the terminal, just a kind of demo, which in an automated manner shows you how FOD can mitigate traffic between the attacker and the victim host in this set. And this we are just now going to see. Only as said, it will be not in the web UI as that, it will be just run in terminal, and the rules instead will not entered via the form we saw just some pages ago, but it will be actually emitted via Python code in the demo script. So now let's go to the terminal here. And if you want, we will do it just from scratch more or less. I will just clone the FOD repo. That will take us a few seconds. So that is similar when you are repeating this yourself. And actually, I have used a command which automatically checks out the specific branch for XRBGP support. You can either do this like this way, or you have do a git checkout later. But we just go there to the checked out directory, and it is now in this. I checked out this specific feature branch for XRBGP support. And what you're just doing now is start the demo script for Docker Compose, and it's just like that. And I will run it in a mode which is not unattended, but which will do it in a single step mode, so I can explain what's going on for the different steps. So first thing is just check whether Docker Compose is ready and the containers are set up. So if you do it yourself the first time, of course, the Docker containers will have to be built. It will take much longer, what we just saw. But the main part I want to show you is the demo itself. And this comes here. If you see something in yellow, that's just an informing headline for the step which is to come. So here we start with the demo proper. Here you just see an overview of, again, as a little reminder, we have the FOD plus XRBGP container, which is peering with the Freertr. And we have the host 1, the attacker, and host 2, the victim, which are routed via the Freertr router. You will see this little picture multiple times if needed. But now comes the part where the initial ping between host 1 and 2 is that, the ping will be the test traffic, the DDoS test traffic. And here we will see how it will be unmitigated. And in the demo here is just made sure, if you restart the script, if there's any leftover rules from previous runs, there is now a Python code run which just removes or deactivates old test rule. And actually that was the case. That was a test rule from the previous run. Now we see what is in the database. Very simple, and we see there is a rule, but it is deactivated now. That means it's no longer exported via XRBGP to the Freertr. So that was just the preparation for the ping, and now we see the unmitigated ping now. Here again, the overview picture over the network. And we will see some statistics, some repeated commands. Here we will see the XRBGP rules. Currently, there is no, this is the XRBGP running together with the FOD on the FOD container, and currently it has no rules exported by FOD. And similarly, and consequently, on the Freertr has no rules either. So we see here three CLI commands on the Freertr. First is the peering here, the FOD, and the next is the database of FlowSpec. And here we see the counters. That was a bit too early, sorry. Here we have there is only a default rule in Freertr for any traffic which has to pass, because there is no FlowSpec rule for mitigating any traffic. Yeah, that was a bit too early, sorry. Now we had the ping here, And you see, actually, there was 5 packets of test traffic from attacker to victim, and they were just went unmitigated. We had no packet loss, 5 packets received. And if we now compare the counters, we will see the same, or execute the same command of the Freertr CLI now as above. We see that actually just this default rule for any traffic had 24 packets after the ping, and before the ping, we can see that there were some packets. Yeah, in the time there were, of course, this includes the ping packets and maybe some PGP traffic, which has been going on as well, because that's counted via this default rule as well. But as you can see, important things of the output of the command are kind of marked in magenta here, so you can easier spot it. So that was the unmitigated ping. And now what's interesting will be the mitigation. And yeah, that will be the part 2 of this demo, the blocked ping. It will be so first you see the schema of the overview, and now we add the blocking rule that is similar as we removed old rules before. But before we just to remind you, we'll see that there is no exabgp rule still, and we still have no FlowSpec rule in Freertr, and consequently only a default rule for all traffic. And now the rule is added into FOD with Python code, and it outputs all the code which actually run in FOD. And here you see the list of all the active rules, or all the rules, and actually this one is active now in contrast to before. And now you will see that it is actually also exported to the local exabgp. So this one is actually corresponding to this one, and further it is pushed via BGP to the Freertr peer. Here we can see it in the database of Freertr for FlowSpec, and here we see the default rule again, but here we see an additional statistics counter for specifically that rule. So what you see here corresponds to this, to here in exabgp and here in FOD. And what's now interesting when the ping will be run is the change of the drop counter for this statistics of the rule that comes now. That will be run the blocked ping now after we have installed the rule. Here then the overview. Again, we see here all the layers where the rule is installed on exabgp as well as on the database of Freertr and on the statistics. And now comes the actual ping, and from the attacker to the victim, but this time we see it is mitigated. It's again 5 packets, but they now are blocked, and this is shown 100% packet loss here, as you can see. And now we see the result in the counters, and you now can see that these 5 packets here have been dropped in contrast to before the counter was 0. So that is basically the whole demo for based on Docker Compose. So I will switch back to the slides, because I have we have a second way to execute this demo, or because there is something called Containerlab. Docker Compose, which we just used before, is, let's say, kind of developer-centric, and it's more suited for developers which want to define Docker containers and so on. Containerlab is an interesting thing, which is more suited to network engineers, and you might know it. I will just show you the main page of Containerlab, if you're not familiar with it. That is similar to Docker Compose, but it is has 2 let's say advantage. On the one hand, it more easily allows you to define network connections in a more easy way. between the different containers. And your containers you can easily include various network devices in. There are a whole bunch of vendor-specific images, and you can easily include them. And that is why we decided to use that as well, because Freertr is included here as well and can be used. And so going back to the slides, so we will do similar thing we saw, but now with Containerlab. And for this, we have a Containerlab specification, which is similar as a Docker Compose set, but easier and more suited for the network, and all these predefined images if you need them. And based on this the Containerlab specification, we again build another demo script, which is available as well, and we just now test. This is similar as the Docker Compose-based demo. It runs only in the terminal, not via the web UI, and the rules are emitted via Python code instead of the web UI. So we already cloned the FOD repo before, and so we can start the demo. And a bit different script, but it's basically in here, and we will again run it in a single step mode so that I can explain what's happening at each step. So yeah, here is just if you run it, you get some reminder how you could clone the repo, but it's just as a dummy. There are actually two possibilities. Either we use the FOD repo or there is the Containerlab Freertr repo, but they contain both the same Containerlab definition and the same container demo script based on it. What we see here is the Containerlab definition as an example to show you. Maybe just explaining, you will see this topology contains actually 4 nodes, similar as we had it before, but here quite simple. You have FOD, you have with XRBGP actually, Freertr, and the 2 hosts, attacker and the victim. And here's just the image referenced, quite easy. And below you have the links in a very nice format, very network centric and not as complicated as with Docker Compose. And you can, yeah, this is just, if you want to extend this with some more complicated example, where you include some predefined images for some router devices or so, that it's pretty easy. But here we just wanted to use Freertr. So this looks like this. The topology will be similar as we have seen in the Docker Compose, only the IP addresses are a bit different because of the network layout and how the differences between Docker Compose and Containerlab. But so the first step is actually to reinitialize the Containerlab. That will actually, the containers are already built here, so it's quite fast, but it looks like this. The Containerlab will give you a nice output after it builds or deploys this Containerlab, and you will see the 4 containers with the Docker IDs and even names, IP addresses, and so on. There's also an inspect command, which has the same output as the final table. So we have to make sure that the containers are really started and up and running before the actual proper demo is started. So just a few moments. It's just some waiting time to make sure that the containers are really started. So now, in contrast to the Docker Compose set, where everything was set up just when the container will run, this is more, we have generic components like Freertr and FOD and the hosts. And now we have to make sure that they are configured. For Freertr, this is done with a already deployed software configuration, but not for the hosts and not for FOD. So first for the hosts, we have to just here's just an overview. We have to configure them regarding the routing and the interface IP address. And this is just done here. for the host 1, the attacker will just configure the IP address and add a route to the Freertr, and the same for the host 2. So now they can reach each other via the Freertr router, which is already configured, and we can see now an unblocked ping between them. And we will just, similar as before, check Freertr's mitigation counters, and there is no FlowSpec rule yet because even FOD is not connected via XRBGP peering yet. And we just see that there is the default rule only, which will let pass all traffic. So now comes the unblocked ping from host 1, the attacker, to the victim host 2, and you can see more or less all the ping packets for 5 were passed except the first one, but that is just because it was the initial traffic and ARP packets had to be exchanged and things like that, and the first packet was just lost. But now connection between the 2 hosts is possible and unmitigated. And we can see this also when we compare the counters. We see that the default packet counter just increased to before. Obviously, there were some packets flow, something else going on, but at least that covered the normal unmitigated traffic. So that was that's gonna come the next part. We have to add the FOD XRBGP peering to the Freertr actually, and this is done with a command: configure the IP address on the FOD container for the interface to Freertr, and then run some configuration code to initialize the peering between the 2. And here's the output of the XRBGP log, and we can see that the peering has been established now, and we can see this also on the Freertr side. If we log on the router, we see that now there is a peering with the neighbor. So now we are prepared for adding a rule, which will be the next step, where we want to have to show the blocked ping. And for this, we add a blocking rule now, similar as we have seen before in the Docker Compose. Before we checked that there are no rules yet in the XRBGP, and also there are no rules as before in the Freertr. Now comes the adding of the rule via Python code, and you can now see it in the database, and it is active rule in the database, and that also means it is exported, given to the XRBGP on that host, and that one transmits it via BGP to the Freertr. We can see it now here in the FlowSpec database of Freertr, and also there are counters installed for that rule. Still at the moment 0 dropped, but now we will do the actual ping from attacker to victim host. Just again see the counters. The rule is installed in XRBGP, Freertr database, and in there's the counters for the rule. Now we see the ping, and now we see it's no longer unmitigated, it's mitigated and dropped, obviously. 5 packets again, and 100% packet loss. And if we now compare this in the Freertr, we see the counters for the rule, and there have been 5 packets dropped now. So all the as a final step, we will now, with FOD still peering with the Freertr, remove the rule again. So here just the overview. So we will now remove the rule, just show that it's still in XRBGP and still on Freertr. Now we remove it via Python code. Then we list and see it's still in the database, but now inactive. in an FAD database, and consequently it has been removed from ExaBGP, and it is also removed from Freertr. There is nothing in the database anymore, Freertr, and there is no counters for instance installed. There's only the default rule for passing other traffic. And so if we now test the ping, it should no longer be blocked. There's the overview. Just again, nothing, no ExaBGP rule, nothing in Freertr. We have the counters, default counters, and now the ping. And you see that now the ping, the attack traffic now goes unmitigated. And that is reflected in the statistics of the default counters. That is just 10 packets, 5 one direction and reverse were just passed. Yeah, that was the demo with Containerlab. Yeah, and that concludes my talk. And if there are no urgent questions, I would pass the voice to Nikos for NeMo. Okay.
Hi everyone, I'm Nikos. I'm from National Technical University of Athens in Greece, and I participate in RER with the main task of integrating the NeMo software solution for protecting against DDoS attacks with the RER platform. So here in this presentation, we will show you our walkthrough of NeMo integration with RER for DDoS attack detection and mitigation that we did along with David. First of all, as previously mentioned by David, NeMo is an efficient DDoS attack protection solution that was developed by DFN. And apart from mitigation that's performed by Firewall-on-Demand, NeMo software is also capable of detecting attacks with various methods that we will see later. The key features of NeMo is that it is open source. It mainly detects anomalies using a Netflow-based approach. Netflow data are collected from the network and analyzed in order to detect anomalies. The software requirements are low. You can install NeMo using Docker containers, or of course there is a second solution that is that relies on Podman for container orchestration, but here we mainly used Docker in our setup. And the operation of NeMo is privacy preserving for the organizations using it, because sensitive data are analyzed locally and not streamed to external collection points. For example, something that traditionally happens with cloud scrubbing providers, where you redirect your whole traffic for them to analyze and mitigate it and return it clean. This is done locally by NeMo. And attack mitigation is based on fine-grained filtering rules. It depends on BGP FlowSpec mainly, and not, let's say, a more naive approaches like plain black holing. So our goal was to integrate the RER platform with NeMo for efficient DDoS attack protection. This effort is ongoing since the starting of the current GN5 phase, GN5.1. We mainly started the whole integration setup in February, and our team strongly collaborated with NeMo engineers. We had a very good contact where we tried to troubleshoot the whole setup. And the outcome of the first year of GN5.1 is that our RER platform can support mitigation rules installed by NeMo components. Here in this presentation, I will provide the proof of concept of this integration. Our setup that took place in my university in Athens, at National Technical University of Athens, in a virtualized infrastructure, consists of 4 components. The traffic generator, which is responsible for forwarding traffic to the attack victim through the RER platform. The RER platform itself that exports monetary data and filters traffic. And NeMo consists of 2 components. The first component is, I called it here the detection component. This is more my terms here. I'm not sure if they're currently used by NeMo, but this is the main idea, that the first component is mainly used for the detection going attacks based on Netflow-based data and triggers attack mitigation requests. The NeMo detection component also includes the user interface of NeMo. And the second component is the mitigation component. It's the software part of NeMo that installs mitigation rules to the RER platform, or in general to the routers of the topology that will be responsible for filtering attack traffic. The specifications of these components, you could see that they didn't involve a lot of RAM, although I exaggerated in the RAM that I used. I'm pretty sure that the detection mitigation component could use much less than 8 gigs of RAM, because the detection component mainly relies on Docker containers, and the mitigation component is mainly a VM with that I think would handle with much less specs. Here you can see a high-level overview of the setup. You can see the 4 components of the setup. You can see the traffic generator that forwards benign attack packets to the RER platform. The RER platform was based, as David said, on the Freertr routing software that we also used for Firewall-on-Demand. The Freertr software is configured to analyze, to sample the whole traffic that is received and export Netflow-based data towards the NeMo detection component, which uses some rules that we'll see later in order to detect anomalies and submit mitigation requests to the NeMo mitigation component via remote procedure call messages. Finally, mitigation rules are installed at the RER platform via BGP FlowSpec. As you can see, there is a closed loop approach where you receive data, you analyze you try to detect if an event is ongoing, and install rules of the mitigation appliance. And besides that, the NeMo mitigation component collects some statistics from the mitigation platform in order to see if the mitigation should stop. Now we'll delve into some implementation details of the components. The traffic generator is very simple. You could just collect some traffic from your production instances and replay it with a tool that's called TCP replay at specified rates. Or what we preferred here, currently experimenting, is that we synthetically generate some data based on multiple software solutions. For example, you could use something that's called HPEC3, the escape, which is a popular Python library, and another tool that is called Mouse. I'm not very sure how it is pronounced. The short, let's say, description is MZ. And you can generate any traffic that you want with these packets and replay it using TCP replay at increased rates. The RER platform, as I said before, mainly relies on Freertr routing software, exports Netflow data, and is responsible for accepting the FlowSpec rules from the NeMo components. In order to configure it, you have, of course, configured the IP network information, the IP address on the router interfaces, configure Netflow, and support for BGP FlowSpec. Now for the NeMo detection component, as I mentioned before, the purpose is to have the user interface where you can control the whole procedure. You can define anomaly detection rules, and in order to detect ongoing attacks, there are various methods that are available in order to detect ongoing anomalies. Of course, we have the NeMo engineers, I think, in the audience if you want to ask something more on that. But a very simple solution is to define thresholds in order to detect violations. And of course, finally, you have the triggering of mitigation rules. In order to install this component of NeMo, there is an automated script that accepts some basic information and configures everything automatically. And as I mentioned before, you can either select between Docker and Podman. Here we opted for Docker, which is more familiar to us. And finally, oops, sorry, the header should be NeMo detection component. I will correct it. It's the purpose is twofold: to install the mitigation rules and collect statistics for error in order to attack the attack mitigation process. The configuration included to establish the RPC communication between the two NeMo components, configure the BGP speaker that is responsible for installing the FlowSpec rules. Here we also used ExaBGP similarly to Firewall-on-Demand. And the final step is a Python script for collecting FlowSpec statistics from Freertr and monitor the whole mitigation process. The main difficulty here in integrating NeMo with the RER platform was to make our router speak with NeMo. For example, for this Python script was specialized for the devices, for the network devices currently supported for NeMo, and we had to provide the support for the routing platform used by RER. In the following, I will show you the DDoS protection, the DDoS protection walkthrough. If I get, do I have time? Oh, okay, I have also prepared a video. I will not show you the slides. You can take a look if you want. I will show you the video that I prepared. In the future, we plan to automate our protection setup with our DDoS protection setup with Containerlab, like the work that David did and presented before. We want to evaluate our setup based on protection data. We're collecting right now data in order to test it. We want to stress test our to see the filtering throughput of the RER platform, and we would like to experiment with diverse NeMo attack detection methods. If you want to reach us, you can reach us by this mailing list. When you open NeMo, this is the NeMo detection component that includes the user interface of our setup. You can see that there is a summary tab that summarizes some open alerts. But the first thing that you have to do is go here in the administration tab and define some detectors. As you can see here, this is my currently defined detectors. For example, two detectors monitoring the SYN TCP packets and UDP packets. These are some very simple detectors. And here you can select the type of the detector. For example, you could select a heartbeat in order to see if a device is up or down. You could opt for a threshold-based approach, or you can do something more advanced. For example, use Holt-Winters method, which is a method that a popular method widely used for network traffic forecasting. Here I will select just a threshold configure detector, and if I go to a defined detector here for monitoring SYN packets, you can see here that there are some parameters that you can choose. For example, you can set various thresholds here. You can monitor per minute or per another interval. You can specify how many packets is critical, warning, information, in order to generate specific logs. Here, I will leave it in a very small number in order to trigger some alerts. For example, here you can change the critical threshold, point it to 10 SYN packets per minute, which is very low, of course, I know it. But here I add it for demonstration purposes. After that, I can save the detector and see if an alert is triggered. Of course, here the idea is that you collect some Netflow-based data from the routing platform, Freertr in our case, and you can see that there are a lot of alerts here. For example, when something started, their duration, things like that. If you go and zoom and select an alert, you can see that there are more details here about the demos, let's say anomaly, and you can also select this option to analyze the alert. You can see some charts here with the traffic. You cannot see here something because it's a demo. Let's say, remember that I inserted a very low threshold, and that basically an anomaly is triggered very easily. You can, after you analyze the alert, you see a lot of, for example, if there is a true anomaly, you can see here more data. You can mitigate the solution. There you can mitigate the anomaly. Here you can specify the range that you want to protect. This is a range of the range of my lab, /24, and you can add more rules here. You can name a rule. You can specify the direction, incoming or outgoing. You can specify the source side that you want to protect, that you want to filter. And basically, going forward, you can add a lot more information about the protocol that you're mitigating, source ports, destination ports, and the action that you want to FlowSpec to do. And before that, NeMo includes another step here. Another step here that you have to request authorization. Here you have to request authorization before you install any rules in the subset. And after you request authorization, you can save this rule and start mitigation. You can see here that if you go on top, there is the status of the mitigation. Here it is inactive. If I go forward, you can see that the mitigation is starting, and in less than 45 seconds, you can see that the mitigation will have started. It will turn from yellow to green. Okay, the mitigation is active. Of course, you would say that these were some very plain rules, but we're currently experimenting with RARE and NeMo, and in the future we hopefully will present to you set up on our production environments. So thank you.
Right. So thank you, David and Nikos, for your work and presentation. Is there any questions from the audience? No, everything is clear. All right. So if you don't mind, let me then provide you a short...
has shown his hand.
Yeah, sorry. It took me some time until I found the raise hand button. The question is more to the Freertr implementation. Is there a way to actually try this with physical machines, and which hardware generally works with it? Because I only saw that there is a limited set of special hardware or switches which is supported by the underlying component. So what is the experience in that? Having RARE run on a machine, on a physical machine, to be a router with maybe running Freertr physically.
Okay, so you that's a great question, because you are anticipating the wrap-up session, but I can answer you right now. So basically, Freertr, as Nikos and David mentioned, it was a subtle sentence, is a routing platform. What it means by platform is that we have a router that is composed by a control plane and a data plane. The control plane is running Freertr, and the data planes are, I would say, can take the form of multiple forms, such as we have a GPDK data plane and we have a P4 data plane. When we are talking about P4 data plane, it means that all the switches that support P4, for example, Intel ASIC-based Tofino switches based off Tofino switch, are supporting this. So this gives you the possibility to run Freertr and the P4 data plane and enjoy this setup with 100 gig port capability. So this is real hardware. Obviously, these give you also the possibility to have with GPDK data plane, you can also use the same setup with multiple 1 gig, multiple 10 gig, or a couple of 100 gig, and maybe more with PCIe Gen 5 new servers equipped with GPDK. This is available. If you don't mind, I can elaborate more during the wrap-up session. Any more questions? So GPDK based is working on all the platform. Well, I mean, all the platforms supporting GPDK are supported. So I think you have a GPDK for FreeBSD, I think. You have also for Debian, for every Linux based. So the question is, can we use SDN controller in this, and what will be the impact? As soon as your SDN controller is able to speak BGP FlowSpec to the platform, to the mitigation platform, you are able to install BGP FlowSpec rules and mitigate traffic. Does this answer your question? Because for me, SDN controller is more part of the trigger component. More question? No? Cool. So let me wrap up real quick and maybe answer more questions afterwards. So as David and Nikos showed you, we have this front component that is doing traffic effective mitigation. This is more or less all of this component can be replaced. Can be changed. If for any reason you have a Nokia router, Cisco router, Juniper router, as soon as it has the possibility to understand the BGP FlowSpec standard and mitigate traffic based on this rule, this is possible. You can freely use Firewall-on-Demand and NeMo with these boxes, first thing. On the other way around, you have also the possibility to use Freertr in pass, connecting your ISBR in your service provider backbone, and also pilot them with Firewall-on-Demand or NeMo. However, nothing prevents you to create a more clever component. I don't know, maybe something based on Gemini, Google Gemini, or ChatGPT-5, whatever. I'm just doing some supposition. This is possible as soon as the result ends up in creating Netflow rules. However, the key component here, and this is, I think, the strength of NeMo and Firewall-on-Demand, is that it is based on raw Netflow data. So if you have a very good raw data quality without sampling, for example, if it is possible, if you manage to solve this producer and consumer problem, you have the possibility to dig into this whole data and derive very clever BGP FlowSpec rule in order to do the effective mitigation. So as David mentioned, you have the possibility to test this on your laptop right now. You just if you have Linux, you install Containerlab, you git clone the repository, and you run the lab as it is described by David, and you have this very cool setup where you have host 1 attack, which is the attacker that is trying to attack host 2 with basic ICMP thing. I know this is a simple setup, but this helps you to understand how to use a Firewall-on-Demand and also how the trigger is working. So in the future, we hope to replace Firewall-on-Demand by NeMo and show you something more complex. One thing I wanted to add between Firewall-on-Demand and NeMo is that Firewall-on-Demand is more a targeted mitigation solution. which means that the user needs to know beforehand what traffic he needs to mitigate. Because, but nothing prevents you to connect Firewall-on-Demand to something more clever that will create these rules automatically. There is a kind of API that allows you to do that. This is the thing. NeMo is more sophisticated in the sense that it can do a more subtle analysis of the traffic and maybe and not only derive a BGP FlowSpec rule related to distributed attack, but also maybe more things related to slow low risk. And this is where the work of the whole community, if we work together to create this pattern detection and complete NeMo, is a great asset for this. So this is what I wanted to mention. Okay, so if this is a setup with 2 routers, but what if you have something that looks like the global P4 lab? Here we have a P4, we have something called P4 global P4 lab that has been presented during Supercomputing 2 weeks ago, I think. So basically, these are all the nodes are P4 switch interconnected using the existing research and education infrastructure on top of 100 gig connection. What if you have a network like that you want to protect? And the cool thing is that it is possible with this solution. With all the hardware you can see, we have Bluefield DPU because the Bluefield DPU, for example, support DPDK, and all DPDK hardware, compatible hardware are supported. So this is not, I would say, slideware. We can help you to create your DDoS mitigation box if you have a very strong server with a compatible DPDK NIC. This is the thing I would like the message I would like to have. The key takeaway before leaving you is that all of these, I would say, fantastic components are open source software. This results on the work of different work groups within GÉANT, security group, NeMo, Firewall-on-Demand, RER. All of these are open source and available for you for free. For free asterisk, because open source software is not only free. You have to invest some of your time. This is an affordable, targeted, and dynamic DDoS mitigation solution. When I mention targeted, is more related to Firewall-on-Demand, and dynamic is more related to NeMo. I wanted to mention affordable because here we are talking about multiple of 5K euros if we are talking about 100 gig mitigation with a 4K entry. And if you have a Tofino 2 box, which is 20K euros, but you will have the possibility to mitigate 12K entry with 12K BGP FlowSpec entry in the P4 code. The thing that is important is related to the question you asked. Sorry, it was Vladislav. Is that the hardware you will select will be able to pilot a data plane, and depending on the data plane, you will be able to mitigate a combination of the outcome will be a combination of bandwidth and BGP FlowSpec entry trade-off. If you want to mitigate with P4 switch, you will be for sure limited by the ASIC, because the solution, even if it is affordable, still has some limitation and won't be the same product as you would have with Palo Alto or Harbor, which is their main bread but I would say core business, you know. But one thing that is really interesting is that if for any reason you are managing a network and you have members, and if you have the possibility to place this infrastructure close to your upstream provider, this is something that is affordable that you can test. Okay. So for more information about RER, just go to docs.rare.géant.org. And if you want to have more guidelines, we have a recipe related to what David presented today. So feel free to visit and go to this page. Thank you. Any question, discussion, idea? Yes, Simon.
Simon Leinenswitch. I just noticed that there were some questions on the Zoom chat, as part of whom were already answered, but maybe they should be repeated so they end up on the recording, because the chat will disappear, I guess.
Okay, so a question from Vladislav. DPDK and NREN 5 and 6 NICs is very something needs to be tested with RAR. I have a good news for you, Vladislav. All the NICs we have are using in the US from Caltech and Starlight are equipped with NOC Connect X6 and 5, and it has been tested with unfortunately Ubuntu 18.04. I say unfortunately because 18.04 is deprecated, but it works. But the good news for you is that during supercomputing, RAR Freertr is running on a specific flavor in a Docker container with DPDK installed with specific kernel capability from the container. And if you know the DPU, the Bluefield DPU, it's a Connectix 7, I think, and it works. And in our lab, we have also a DPU from Marvell Octeon that has been recently staged and installed by our colleague from Switch, Alexander Gall, which is the same as the Bluefield GPU, Marvell Octeon, with I think it's 24 cores, something ARM CPU, and it has been working. We are planning to streamline GPU installation simply because the container form flavor was quite easy to deploy. And sorry, if you look at the map here, we have some of the new nodes are running GPU, and here obviously they are gray simply because they are being staged, but we can confirm it's working. Sorry. What are the other questions? I'm using a short intro on how to use Freertr and DPDK. Oh yes. So basically, if you just look at the documentation, and also we can have a quick session, and we can show you how it works. So Jérôme, out of you, can you share what is the typical Netflow sampling rate used by NREN that uses NeMo? I think this is a question for Eugene, maybe.
Yeah, Eugene has already answered in the chat.
Sorry. Sorry. My bad. Well, in some situation, for example, if you consider ESNet from the Department of Energy, they have a specific Netflow project that is called Heritage, and they have unsampled Netflow provided by P4, their P4 code running on FPGA cards.
By the way, the answer that Eugene gave was usually in the range of 150 to 500. So one in so many packets, with 300 being pretty popular, just for completeness.
Thank you, Simon. And thank you, Eugene. Any more questions? If not, I would like to thank all people involved in this very, very interesting work. It was a very tremendous effort from everyone. from the team. Again, it's a collective work package activity result. So all of this is available for free, open source. And if for any reason you would like to know more, just don't hesitate to reach us via the mailing list. And we can engage discussion on how to elaborate some use case that you can have in your context. With that in mind, I would like to again thank you all, also the audience for their presence and interest. Feel free to reach us, engage discussion. So, sorry, communication is key here. You're more than welcome to reach us.
Thank you very much, Frédéric.
Thank you, and have a good day then. Bye-bye.
Bye-bye, everyone.